Sonio. Yeah, so last class we have finished with rotational mechanics. Today we'll be starting off with heat and thermodynamics. So if you see entire heat and thermodynamics, it has actually 5 subparts. The first was thermal expansion. Then we have calorimetry, and then we have KTG, then we have thermodynamics, and then we have heat transfer. So there are total 5 parts. But the first 3 are easy. Right? They're not big ones also. Concepts are also little, on the easier side. Thermodynamics is it looks like chemistry, but there is a difference with the sign convention. So those two are the main ones, thermodynamics and heat transfer. So we'll start off with the easy ones, thermal expansion, and then we will go ahead slowly. So the first thing, force between molecules. Consider we have two atoms. Let's say this is a molecule 1. This is your molecule 2. And we have electrons here. So now initially what happens if you see the nucleus is positive charge and the electrons are negative charge. The nucleus 1 attracts the electrons of molecule 2 and vice versa. The nucleus 2 attracts the electrons of the molecule 1. So if you see, there is actually a slight attractive force. Force is attractive in nature. In chemistry, you studied this thing as called van der Waals forces. Next thing, if the molecules are, now what you do, if you push the molecules a little closer, attraction will still increase. But if you keep pushing the molecules closer and closer and closer, at one point, the nucleuses will start repelling each other. Because both the nucleuses are positive charge and all the charge is located at one spot, the repulsion becomes quite high. Force is repulsive in nature. That same attractive force suddenly becomes repulsive in nature. So if you actually try to plot a graph between force and R is the distance between the molecules. This is how the graph would look. Look at this graph. At infinity, when you're very far, that is R is infinity, the force is almost zero. As you get closer, as R is decreasing, means you're getting them closer and closer. You can see force is becoming more and more negative. So the negative force indicates it is attractive in nature. But if you push them too close, the force becomes repulsive. So F has become positive. So if you see here, there is one particular spot here where you get a maximum force of attraction. This is what we call as bond length. So now from this logic, if you try to observe, see what happens. Molecules are here. So if you try to, pull them away, if you try to pull them away from each other, it means if you try to elongate them, they will come here. So what will happen? Force will decrease. So it will try to again come back to this position. If you try to push them towards each other, that is, if you try to compress a body, again they'll come here, r becomes small, so they will again attraction force will decrease. Again, they'll try to come back here. This lowest point, right, kind of behaves like a stable equilibrium. If you try to elongate a body or compress a body, the attractive force decreases. So they will try to come back to the maximum attractive force. So this is the reason, right? A body will always resist deformation. Whether you're trying to elongate a body or compress a body, it will try to resist both of them. So if you see in a lattice, we have multiple atoms there. So everyone is attracting each other. So the net force is zero. Now, if you try to disturb this, imagine you try to push this molecule slightly to the right side. If you push it here, what will happen? This attraction forces will, decrease. So they will dominate and they again try to come back. It's kind of like springs. Hmm, So it increased, right? Navihan.
Yes, sir. I think I heard decrease also.
Yeah, no, it did increase more negative, and then it started decreasing again, became positive. Clear this? If you bring them too close, the nucleus will start repelling. All got this, everyone? So next time when you think, right, why does the body, whenever you try to, if you take a rod and try to stretch it, it will resist you. If you try to compress, it will resist you. Getting it? So bodies actually resist deformation. Whether you try to compress them or elongate them, they will always try to resist deformation. Again, there are little exceptions here and there, but generally this is what most of the things do. Now, if you look at this thing, molecules are always in a constant state of vibration. So if you give more temperature or more energy, they will oscillate more. The kinetic energy is proportional to temperature. So whenever you heat up a body, the molecules have more energy. Now they vibrate with higher amplitudes. Think of like this. Let's say we have a bench there in your classroom and three people can sit, right? And when let's say one of your close friend is trying to come and sit there, what will you do? You'll all adjust and four people will try to sit. But imagine if your enemy friend is trying to come and try to sit. What will you do? Even if there are only two people in the bench, you'll occupy the whole bench. You won't let anyone sit, right? You'll say a place nahi hai, isn't it? So something of that sort. So what will happen? Because the each one is trying to have a higher amplitude. So initially they used to occupy this much space. Now they want to occupy this much space. So what will happen? The molecules start pushing each other, and in this process, the bond length would actually increase. So if you actually try to see the graph again, the force versus R graph, if this is temperature T1, this would be temperature T2. You can clearly see the bond length R2 here. So T2 is greater than T1 if you have higher temperature, then R2 becomes greater than R1. So the molecules will need little extra space in order to be in a natural state. So whenever you try to increase the temperature of the body, this is what would happen. So at temperature T, let's say the molecules are occupying this much. When you increase the temperature, T plus delta T, so the bond length increases. So when you take a rod here of length L, temperature T, that same rod, when you increase the temperature to T plus dt, now because each molecule is pushing it, there will be a slight increase in length dl. This would be at temperature T plus dt. So basically here dl is the increase or change in length due to temperature change dt. We will talk about this again in elasticity, but we have an important statement here. That means this L plus dl, which we got, is actually the new natural length. So when we say the body ka natural length is, L, for different temperatures, you have different, natural lengths. What do you meaning of natural length? That is a state where you're in a pretty relaxed state. Think of like this. Let's say if I catch your cheeks and pull them, it hurts you. Why does it hurt? Because that is your natural length and I'm trying to elongate them forcefully. But imagine you eat a lot of food and you become fat and your cheeks become big. Does it hurt? Because that is now your new natural state, isn't it? By eating a lot, you put on weight and you got more fat or something and your cheeks become bigger. So now that is your new natural state. Now in both the cases, didn't the cheeks become bigger? But in the second case, you don't feel any stress. But in the first case, when you pull them forcefully, there is a lot of stress. Getting the difference? So same way, when you increase the temperature, the molecules are pushing each other and they automatically adjust and they get this new length so that there is no stress between them. So this would be the new natural length at the temperature T plus dt. So when you say natural length, meaning that is a state where you don't have any stress. The molecules are in a pretty relaxed state. Clear with this, everyone? Then, great. So consider the length of the rod increases by dl when temperature changes. So we can write dl. So dl is proportional to dt. So more the temperature change, more the rod will expand. Dl is also proportional to the length of the rod. If there are 100 molecules and if there are 1,000 molecules, and if each one elongates by 1 nanometer, shouldn't the second rod have more change in length? The bigger the rod, more change in length you get. More temperature change, more length you get. Now be careful, this proportional here is a symbol for proportionality. When you combine this, you end up with dl is equal to L alpha dt. And this alpha is something else. This alpha is coefficient of linear expansion. Unfortunately, both of them look same, so be careful what you're writing there. So we can define alpha is 1 by L dL by dt. So what this thing tells you is, what is the change in length per unit temperature. So we call it coefficient of linear expansion. This depends on the nature of the material. For example, copper has more alpha than steel. So copper molecules are more, can easily, move away from each other or expand more than steel. So the meaning is this. So higher the alpha, more easily it can length change the temperature. Now, if you actually look at this alpha ka value, it is generally very small. Alpha is in the range of 10 power minus 5 per unit degree. The meaning of that is, if you take 1 meter rod, right, and if you change the temperature by 1 degree, then the change in length is 10 power minus 5 meters. Making sense? That is the thing of alpha, change in length per unit temperature. So when you change the temperature by 1 degree for a 1 meter rod, the length will change by 10 power minus 5 meters. It's quite small. So example, if you take alpha of, there's a material called invar steel. This is what we use to make instruments. This thing has 10 power minus 6. So lesser the alpha, the better, because you don't want your instruments to get messed up because of temperatures. So now again, getting back to this formula, we got dl is equal to L alpha dt. If you send the dt this side, we get dl by L is equal to alpha dt. Integrate on both sides. This will go from L initial to L final. This will go from T initial to T final. This will be ln L. L initial to L final. This will be alpha T. Limits will be from T initial to T final. This can be written as ln L final by L initial alpha delta T, where delta T is T final minus T initial. You can expand this thing. So L final will be L initial e to the power of alpha delta T. This is the actual relation between the final length and the initial length. You get an exponential function. But be careful. So let me just write it down, the whole thing. So the final length will be initial length exponential power of alpha delta T. Right? This is normally valid, but rarely we do use this. It does come, mains and bits method won't come, but especially advanced or some perspective, right? So use this if alpha delta T is comparable to 1. Technically, this is right, but reality, this is a little difficult to use that exponential and all. So we have an approximation, but let's see this before going ahead. Have a look at the derivation, what we did. And second thing, we also limit our study for very small temperature changes like 5 degree, 10 degree. We don't really study for 100, 200 degrees. Most of our studies are like that. When you make the temperature ranges or anything very big, things won't look so beautiful. This proportionality only might not hold. The basic assumptions only will start going wrong if you take a temperature change of 100 degrees or 200 degrees. But then again, we'll not get there. Clear with this? Then, if you go a little mathematically, if you see an e power x ka series, e power x can be written as 1 plus x by 1 factorial plus x square by 2 factorial plus x cubed by 3 factorial and so on. This is an exponential series. So e power alpha delta t will become 1 plus alpha delta t plus alpha delta t square by 2 factorial and so on. Now, like I said, alpha is very small, 10 power minus 5. So if alpha delta t is much, much less than 1, right? So then we can neglect higher power terms. Alpha delta t square, right, will be very small. If alpha delta t is 10 power minus 5, this is 10 power minus 10. Therefore, higher terms can be neglected. Then your formula becomes, so L final is L initial e power alpha delta t. This becomes L final into L initial plus 1 plus alpha delta t, alpha delta square by 2, and so on. We neglect this stuff. Then you end up with a formula. L final is equal to L initial into 1 plus alpha delta t. Similarly, delta L will be L final minus L initial, which is L initial alpha delta t. There. So this is what we use. The change in length is L initial alpha delta t, and L final is this. So this is valid. Getting it? But again, for small alpha delta t's, this is valid if alpha delta t is much, much less than 1, which is true for most of the cases. So remember this thing in the exam or in the question, if nothing is mentioned, assume this is right. Don't use that exponential thing. In order to use that exponential thing, you have to be pretty sure in the exam that the question where alpha delta t is big. So they will give you the values for alpha and delta t. If I don't mention anything in the question, if I just give in terms of variables, we'll always assume this is the case. If nothing is mentioned, then we use this. So that exponential thing is mostly an advanced kind of thing, means in between they won't even touch that. So be careful with that. Now, in 99% of the problems we use this only L into 1 plus alpha delta t. I'll show you an exponential thing also later on, but that's an exception. That is valid only when alpha delta t is comparable. Yeah. So this is what you actually learned. So the whole story which I'm telling you from last half an hour is this. L final is L initial into 1 plus alpha delta t, or change in length is L initial alpha delta t. We are going to play with this thing in the whole chapter. But I hope everyone is clear why materials expand. Let's see some questions. Let's see the first question. We have a rod here placed on a smooth surface. Length of the rod is L. Coefficient of linear expansion is alpha. Now see, I didn't say anything about that. So alpha is small. This is your center. This is your point A and this is your point B. This distance is L by 4. This is L by 2. Now what you did, you started increasing the temperature. If temperature increases at a rate of T degrees per second. So every second you're increasing the temperature by T degrees, maybe 0.1 or 0.01 degrees. Now tell me one thing, when you increase the temperature, what will happen? Rod will expand. If you keep on increasing, what will happen? The rod will continuously keep on expanding. That means point A and B are moving. Find velocity of A and B. If the rod temperature is continuously increasing, that means A and B will be continuously moving. That means they have velocity. Find the velocity of A and B. In case you thought mechanics is over, yeah, it is never over. Mechanics will keep haunting you. Think I'll give you a minute. Should I show you one? 30 seconds more. Solve. People are sleepy. People are eating. It's like movie theater types. At least let the teacher feel like, yeah, my students are working so hard. If you're just eating like, as if it's a movie theater, popcorn types. I hope at least people are eating good. क्या हो गया? Devansh not well. He just woke up from the sleep. Let's see what's happening here. First thing, are there any external force on the system? When you heat a body, are you giving any forces? No. Since F external is zero, center of mass does not move. Meaning the center of the rod will be at the same place. The rod will expand on both the sides. Na? See, rod will just not expand on one direction. The rod will expand on both the directions, isn't it? Because you have to keep the center of mass at rest. Since F external is zero, center of mass is unaffected. So, delta L is L alpha delta T, that is still right. But you're forgetting the center of mass, the center will not move. This is at rest. So when the rod tries to expand, it will expand on both the directions. Making sense? So now if you take your point A here, this would be your L by 2. So let's take like this. So what is the change in length for XA? The displacement of A will be only because of this expansion in the rod, right? Doesn't make sense. The reason why A will expand is only because of this. So delta XA will be equal to the length L by 2 alpha delta T. Be careful, I'll use capital T for temperature and I'll use small t for time. Now, if you divide delta XA by delta T, this will be L alpha by 2 delta T by T. This becomes velocity of A. Delta T by T is given, which is T. That is the change in temperature per unit this thing. And what is the direction? I cap. Making sense, everyone? Similarly, when you talk about B, the reason why B is expanding is only because of this length. Think of like this. See, how much your elbow moves will depend on your motion from shoulder, right? Just because your wrist is moving, will your elbow move forward? You're getting what I'm saying? If you're standing here, look at this thing. If you, when you look at your hand, when you stretch your hand like this, your hand has two parts: the shoulder, the elbow, and the fingers. How much this point will move will depend only on how you're moving this part, isn't it? Your wrist has nothing to do with your elbow. No matter how much you twist your, wrist, your elbow is not going to move, isn't it? So same way, how much B will move will depend only on this green part, which is L by 4. It doesn't matter how much is this part moving. I can do the same thing here. So delta XB will be L by 4 alpha delta T divided by time delta T and delta T. This becomes velocity of B, which is L by 4 alpha T naught. It's going backward to minus I cap. So there, that is the main thing there. The center of mass is not going to move. Since the surface is smooth and there are no external force on the system, the center of mass has to be there, and everything else will, stretch on both the sides. Is this clear, everyone? Let's see one more. So there. So this is how you can frame questions also. Let's say we have a rod here. So this is fixed on this side. The left-hand side is fixed to the wall. So from here, you connected this to a pulley. We have a block like this. This thing is L and alpha. Same thing. Find velocity of the block if temperature increases at a rate of T degrees per second. This is smooth, but the left side of the rod is fixed. T naught is I gave no. Okay, T degrees per second. I thought it is T naught. Okay. That T degrees per second only is T naught. Let's get this. So what's the difference between this and the previous problem? In this case, you can't expand on the left, right? So all the expansion will happen only in one direction. That is the only thing. Get it? Rigid body constraint, everyone. String constraints. Hmm. Right, Vihan. Others, get it? The 30 seconds. L alpha t by 3. So if you consider this point to be A, now we can just see delta xa by delta t will be L alpha delta t by delta t. So we get VA is equal to L alpha t. Now we know from string constraints, if this is tension T, this is tension, this is tension, this is tension. So this will be 3T. Let the block go VB down. You can see that every time the pulley goes down, it will require 3 strings. Na? Means if I give X string, it will move only X by 3. You can even see from the diagram. So that will be T into VA minus 3T into VB is equal to 0. You can see this and visualize, but you can also use this string constraint and finish it off. L by 3 alpha T. Make sense? So whatever A moves, it has to provide the string for 3 strings. So it will only go 1/3. And
This question, won't the center of mass be moving?
it will be moving. क्या problem था? Why? What is the problem? You hate center of mass moving.
Sir, so with that, won't A move with a greater speed?
Why does the center of mass move?
Because it is because
Who
it is
is there? Because there is a wall, na God here.
uh,
So there is an external force. So what is the problem? All the expansion that will happen, why will the expansion change? Total change in length of the rod कितना होगा? L alpha t. Getting it? So instead of expanding left and right, now all the expansion will happen only to the right, na? तो what you're saying is true ना? तो सेंटर मास मूव कर रहे तो इसलिए फास्ट मूव करना चाहिए. पहले कितने से मूव कर रहा था? L by 2 ना? Now how much it is moving? L ना? There it did move more. You're not wrong. So what's the doubt? Clear. All got this? Next one. There, questions of physics are not tough, but they're a little different. Let's say mu is greater than tan theta. You kept a rod on top of it. We have a rod mass m, length L, and alpha is a quotient of linear expansion. So first thing, when temperature increases, a point on the rod does not move. Point P so there is a friction here. Mu greater than tan theta means greater than repose angle, so it won't slide actually. So when you increase the temperature, we observe there's a particular point P on the rod which does not move. Similarly, when temperature decreases, point Q does not move on the rod. Find the position of P and Q. So where is this point P? Where is this point Q? Meaning options will be like, it's at a distance of so and so from the top, from the middle it is so and so. You will get something like that. Find the position of P and Q. Now even better. Now you decided if temperature increases and decreases and continuously. So first you increase the temperature, then decrease, then increase, and so on. If you keep doing this non-stop, in which direction will the rod move? Or what will happen to the rod? Will it climb the incline? Will it come down the incline? Will it oscillate, or it does nothing? Describe the motion of the rod. So will the rod climb up? Will the rod come down? Will the rod stay there? Will the rod oscillate? It goes up, comes down, goes up, comes down, something like this. Let's get the first part. So C is connected to A and B. Hope the question was clear. Someone didn't get the question, please ask. First and second are kind of related. That means you're saying center of the rod, no? Why to use such fancy terms, center of mass and all? Just say center of the rod. There, let me help you with one. You do the first second part. Now, interestingly, in this thing, right, you don't care about the del alpha delta t. Now, what did we say? We said there is a point B is not moving. Agreed? So, when I take this rod, let's say this is point P. Now, we are saying P is not moving. Okay? Let point P be at rest. Now, when you say this point is at rest, so what are you saying exactly? You are saying this part here is going up, na? When you increase the temperature, this will expand up. Let the distance be x. Now you tell me, if this thing is sliding up, what is the friction on this? Up or down? The surface is rough and you're sliding up. The friction will be which way? Up or down? Down, right? Friction will be this way, F1. And how much is that? Mu, mass of this part, which is m by L into x, that is the mass of that piece, into g cos theta. Mu mg cos theta. Is that making sense, everyone? Similarly, if you look at the lower part, which is L minus x. Now, if P is not moving, so this is doing what? This is expanding down. If this thing expands down, how will the friction be? Friction will be upward. F2, which is mu, mass will be m by L into L minus x into g cos theta. Now, what are these two frictions doing? Don't forget, you also have your own weight, mg sin theta. So on the entire rod, the friction is not in the same direction. So from here, you can clearly see F2 is balancing both F1 plus mg sin theta. So F2 minus F1 is mg sin theta. If you subtract these two, you end up with mu mg cos theta by L. L minus x is mg sin theta. Mg goes off. L minus 2x is equal to L by mu tan theta. Send x that side, so you'll get L into 1 minus tan theta by mu. There. Now, if they give you in the exam, let's say if they give you mu is equal to 3 tan theta, I can substitute there. That will be 1 minus 1 by 3. So that would be L by 3. L by 3 from the top. So you'll get something of that sort. This is the distance of point B from the top. Interestingly, if you do for Q, Q में क्या होगा? if you say this point is Q, this part of the rod is doing what? It is compressing, right? This would be friction F1. If I take this to be L minus X, this would be mu m by L minus xg cos theta. Because when temperature decreases, it contracts. So this would be F2. This is X. Mu mg x by L cos theta. And then you have your same mg sine theta. So even this, the equation here will be the same thing. So F2, here F1 will balance. I think, let me just change the variable. So let's call this thing F2. Let's call this thing F1. There, again, the same equation you'll get. F2 will be F1 plus mg sine theta, X will come same. But the X is from the bottom now. You're getting it? P is X from the top, Q is X from the bottom. So be careful. This is Q. Check it out. So you get the same answer, but P and Q are not at the same point. P is on the top and Q is at the bottom. You can definitely see here it is L by 2 minus something, means it is definitely above the center, and that guy is definitely below the center. Is this making sense? And if you observe here, I didn't use anywhere L alpha delta T. You don't need it. So the only concept here is because that point is not moving, that means the rest of the rod is either going away from the point P or they're coming towards point Q. Now, because they're going in direction, friction will act opposite to them because it is sliding on the floor. So the difference in friction will balance mg sine theta. It's a good question. It's not a tough question to solve, but it's a little difficult question to figure out what the hell is happening. So this is what I keep saying, it's a tough question, but easy to solve. Figuring out is tough, but once you figure out it is just 2 steps, you'll get the answer. Question is still not over. Now, if I increase the temperature, decrease the temperature, increase the temperature, decrease the temperature, how will the rod move? If I continuously keep doing this, what will happen to the motion of the rod? Think about it. See. So let's say initially rod is here. So P is here. Okay. Now you increase the temperature. Now, if you increase the temperature, center of mass will move which way? P is at rest. So center of mass will come down. Make sense? There. That means whenever you increase the temperature, the center of mass of the system will come down. This is point Q. Now let's say if temperature decreases, what will happen? It will contract, right? Rod contracts. That means center of mass will still come down. You're getting the catch? Because P will not move now. So this point will not move. That means everyone else will go away from P. So center of mass is on the other side, it will go down. In this case, Q won't move. Everyone will contract towards Q. That means center of mass will come towards Q. Is that making sense? So whether you increase the temperature or decrease the temperature, rod will always go down. So center of mass always goes down, whether you increase or decrease the temperature. So eventually it feels like the rod is crawling on the floor. Eventually it will fall down. So imagine, if someone makes a house with some steel sheets or something, and if you have some brick or something on top of it, and during summer, right? Morning it is hot, evening it is cold, morning it is hot, evening it is cold. Eventually, this brick, right, will start dragging, and eventually will fall down. It will start crawling, like it feels like as if it is crawling on the floor. Clear, everyone? Got this? Easy one. So the only thing that I used here is if P and Q are at rest, the remaining rod will either go towards P or away from P. So that is the only thing there. Any doubts on this? There, it's a question based on friction. Next one. We have a composite rod. This is L1, alpha 1, L2, alpha 2. So exam they'll simply say like this, find alpha equivalent. The meaning of this thing is, if we replace this rod, so if you want to replace this with a single rod, whose length will be L1 plus L2, made of uniform material, L1 plus L2, alpha equivalent. So they're asking find alpha equivalent. That is the meaning of alpha equivalent. If these two rods were made of same material, what should be that alpha so that I get same elongation? This is an easy one. Get it? You'll get it in a step. It's an easy one. So they should have same change in length. So whatever elongation you have for that composite rod, it should be same for this big rod. So L1 alpha 1 delta T plus L2 alpha 2 delta T must be equal to L1 plus L2 alpha equivalent delta T. Therefore, alpha equivalent is L1 alpha 1 L2 alpha 2 by L1 plus L2. There. Easy one, but keep this in mind. They won't tell you all this story that, take a one rod of L1 plus L2. They'll simply say alpha equivalent. You should figure out this part. Quite a useful one. This will again come in elasticity. There will use you equivalent Young's modulus. So you do get questions of this sort. Clear with this? Easy? Clear, na, Soham? Arya? Ahana? Clear? Next one. Maybe got an isosceles triangular frame. Let this be L2, alpha 2, L2, alpha 2. So those two are equal. This is L1, alpha 1. This is point A, this is point B, and this is point C. From here, if you drop a perpendicular imaginary line, CD. So the question is, find the condition. That means find the relation between L1 alpha 1, L2 alpha 2. If CD remains constant. Means no, whether you increase or decrease the temperature, CD should not change. Again, remember, if nothing is mentioned, alpha delta, it is very small. You can use your binomial approximations and all. You can neglect all that alpha square terms. Just to give you an idea, what do you mean by this? When you increase the temperature, what will happen to AB? AB becomes big. AC also becomes big, but the height doesn't change. Getting the meaning of it? When you increase the temperature, everyone is increasing, but the height should not change. Similarly, when you decrease the temperature, AD becomes small. This also becomes small, but height won't change. You do anything, height should not change. Then what is the relation between L1, L2, alpha 1, alpha 2? Get this. Think, I'll give you a minute. Let's see. In this, if you look at CD, so CD square will be AC square minus AD square, Pythagoras theorem. So this is nothing but L2 square minus L1 square by 4. Right? Now, if the temperature changes by delta T, then your AC becomes L2 square into 1 plus alpha 2 delta T whole square minus AD will become L1 by 2, that is L1 square by 4, 1 plus alpha 1 delta T square. Remember, this is still equal to CD square. This must be still equal to L2 square minus L1 square by 4. No? That was the whole theme, isn't it? Your length should not change. Now, when I expand this, you will observe L2 square, this will be 1 plus 2 alpha 2 delta T plus alpha 2 square delta T square minus L1 square by 4, 1 plus alpha 2 alpha 1 delta T alpha 1 square delta T square is L2 square minus L1 square by 4. Now you can clearly see here, this guy will cancel with this and this. This and this we can neglect them because higher terms. If alpha delta T is small, these are much smaller. And then you are left with 2 alpha 2 L2 square minus L1 square by 2 alpha 1 delta T is equal to 0. Now that thing has to be 0. So 4 alpha 2 L2 square is alpha 1 L1 square. There. If you satisfy this condition, CD remains same. Check. The answer should not have delta T, isn't it? No matter whatever is the temperature delta T, if this coefficient is 0, independent of delta T, you'll always get the same length. Check. Any doubts on this? All clear? Next one. Clear, na? Ojas, Vignajit, Sharman? Clear, na? Ariman? Devika? Got this? Next one. We got a rod here. X is equal to 0. X is equal to L. Initial temperature is 100 degrees Celsius. Case 1. The coefficient of linear expansion is alpha naught into T. It's not constant. Alpha naught is constant and temperature, T is the temperature. Means when the temperature increases, alpha increases, meaning this rod will expand with more and more temperature. T is temperature in Kelvin. Case 2, alpha is equal to alpha naught x. So this is something else. This is changing its position, meaning the left-hand side of the rod will expand less compared to the right side of the rod. The more the x coordinate, more the alpha. I hope you're getting both the cases are different. First one is depending on temperature. So if you increase the temperature, the whole rod will expand more and more. Case 2, it is depending on the coordinate. The right side, the more the x, the more it will expand. So these are two questions. So find the change in length. When temperature becomes 200 degrees. Let's get this. We fell into the trap we had. Look at the first one. alpha is equal to alpha naught t. So in the formula, dl is equal to L alpha dt. Now be careful here. We are taking alpha is small, so L is almost constant. So now dl, L will be alpha naught t dt. So far it is still fine, nothing wrong. Now when you integrate this, you will get integral dl is equal to L alpha naught t dt. Now this is where everyone goof up. What are the limits? What are the limits? This will be L initial to L final. Temperature is in Kelvin. Means your limits will be 373 to 473. That's it. Just be careful with that. It is not 100 and 200. There are multiple times that even J people themselves have messed this up few times, and they had to give bonus marks. So the limits temperature should be in Kelvin. Generally, delta T में problem नहीं आएगा, but in squares you will have an issue. So this will be change in length is equal to L alpha naught T square by 2. Limits will be from 373 to 473. So this would be L alpha naught by 2. 473 square minus 373 square. Not a great number, but yeah. Now how to do for the B part? B is an interesting technique. Listen to this carefully because the same thing you're going to use for other thing. T change is 100, so L wouldn't be, yeah, Purja, but we can ignore it. We can't solve with that. No, but if you see na, alpha delta T must be small, na? Alpha is 10 power minus 5. Even if delta T is 100, 10 power minus 3 is still smaller than 1.
But sir, if we take it to the other side, we get ln में आता है, so sir, we would get an answer, right?
You will get an answer with the same thing. You will still get the same thing, but usme bhi you have to take temperature in Kelvin. Right, Poroja?
Yes.
Meaning you're saying I will take ln and I will try to do. Do it now, you'll get the same thing. See, understand one thing.
Yes, sir. Yes, sir. I got it, sir. Because alpha, yes, sir.
You're getting it.
Will be
ऐसा नहीं है because हाँ वो alpha delta t square का negligible हो जाएगा. See, both the formulas are not wrong. If you ask me, the exponential formula is actually more right. You approximated and created the second one, isn't it? So this is how we do the second one. See, now here the problem is what? Every piece has a different alpha. So this is how we do these kind of questions. At a distance x, take a small slice dx. Now this slice is so small, I can assume it is almost uniform. So this is what we are going to do. We are going to find that small elongation dE in that small slice. So dE is change in length in dx segment. Therefore, now delta L will be dE, L will be dx, alpha delta t. Making sense? You can't find for the whole rod in one go because alpha is changing for every point. So you take such a small dx, you can assume the alpha is same for that dx. So this would be E is equal to integral alpha will be alpha naught x dx delta t. Now remember, delta t is actually constant here. It's 100 degrees. This will be alpha naught into 100 by x square by 2, 0 to L. So this will be 50 alpha naught L square. Now delta T, whether you take in Kelvin or Celsius, it is the same. It won't matter. But when you have a T square function, it matters. Hope that was clear. T final minus T initial, whether because you're just adding plus 273, right? The difference won't matter. But when you have a square or something, it does get affected. Clear? Any doubts on this? Let's see one more. We have a square frame, side L. Square frame, not a sheet. Alpha is equal to 0.1 degree per Celsius. Find change in area when temperature changes by 10 degrees. Puroja, you fell into the trap. Look at the alpha ka value there. This is what I'm saying. When you see the word alpha 0.1, that should ring your bell. Alpha ka range is generally what? 10 power minus 5. This is 0.1. So if you look at here, alpha delta T is 1. This is comparable to 1. You can't use an approximation. Therefore, we have to use the formula L final is L initial e power alpha delta T. This is what I'm saying. If I give you the value of alpha and delta T and you can check, then use the exponential formula. If you can't check, if the alpha value is not given, then assume it is small. So this would be L final is equal to L into E. So change in area will be E square L square minus L square. So that will be L square into E square minus 1. Now, if you try to use the normal formula, you will get L into 1 plus alpha delta T will get 2L. You will get 4L square minus L square, you'll get 3L square. Unfortunately, that also will be there in the options. That is different actually. So E square is 2.7 ka square and this is something else. So be careful here. Alpha delta T is big. So it should ring alarm bells, when you see that word alpha is 0.1. That was a trap. In the previous questions, if you observe, I never talked anything about alpha, so it is small. But again, they won't touch this in mains or bits. Clear with this? Take a break, come back with 7.5. Any doubt so far? Okay, come back in 10 minutes. So it's lost you again. हमको GPS लगा देता हूँ so that they won't. सारा नहीं 8-10 तक है. So let's say we have a 1 meter scale. We have and alpha s is the coefficient of linear expansion of steel. We also have 1 meter wooden stick. Alpha of wood is 0. Means wood will not expand if you change the temperature also. And then we also have a 1 meter copper rod. And alpha copper is the expansion of coefficient of linear expansion of copper. Now this scale, right, is designed to work properly at 30 degrees. So at 30 degrees, the scale shows 1 meter for the wooden stick and the copper rod. So the question is find the reading when temperature becomes 40 degrees. So this scale, which gives you the proper values at 30 degrees, if you operate this at 40 degrees, it does get messed up. Now, if I use the same scale to measure the wooden stick and measure the copper rod, what will it show? Did you ever think about it? Why in your laboratories there is an AC? It is not for you to be comfortable. Getting it? It is not so that you can sit comfortably in the AC room and do your practicals or lab experiments, so that is all bullshit. Because most of these instruments, right, are designed to work around 24, 25 degrees temperature. Now, if you're using those instruments, let's say, which are developed in Europe or something, cold countries, and if you use it in India when temperature goes to 40, 45, you start getting all weird readings. So the ACs are there for instruments. Getting it? So we students don't have any value in the lab. Instruments are more important. So there, let's get this. How do we do this? Take a minute. Hope the question was clear. Let me ask you this way. Imagine you and I are same height. Next day I became double. What will I think about you? You became half, right? If I become triple, you became one third. If I become 10 times, I think you became 1/10. So you're seeing what is happening? By whatever factor I increase, I think you decrease by the same factor. But let's say you become double and I become triple, then what will I think? First, see, you became double. Now, if I become triple, I will think you became double and then you become one third, right? Yeah, I'll think you're two third, no? Then is that making sense? So the formula goes like this. So the reading of the scale is the length of the body at the new temperature by the factor by which scale length increases. Factor, huh? There, you can remember this. This would be a more general result. So when you take the scale, which is 1 meter, and when you increase the temperature, this will become 1 into 1 plus alpha steel delta T. So the factor is this. So the scale has increased by a factor of 1 plus alpha is delta t. Clear? So now if you take the reading of the wood, so if you use this new scale to measure the wood, alpha delta t is 10 degrees here. What is the length of the wood? The length ka wood will not change its length 1 meter. By scale will be 1 plus alpha s delta t. So we can use binomial approximation here, 1 plus alpha delta t minus 1. This is approximately 1 minus alpha s delta t. Exam में options will be like this only, 1 minus alpha s delta t. In case you don't remember, binomial approximation, I think I told you before, if you have 1 plus x whole power n, this can be approximately written as 1 plus nx if x is much less than 1. Example, if you have 1.003 whole to the power of 4, this can be written as 1 plus 0.003 to the power of 4. You can approximate this to 1 plus 4 into 0.03. This would be 1 plus 0.012. That is the meaning of it. If x is very small, you can use this binomial approximation. And like we know, alpha is delta t is small. What will be the reading for the copper rod? Now copper ka length actually changes, so that will be 1 plus alpha copper delta t by 1 plus alpha steel delta t. This would be 1 plus alpha copper delta t by 1 plus alpha s delta t whole power minus 1. Again, we use binomial approximation. 1 plus alpha copper delta t, 1 minus alpha steel delta t. Multiply, you end up with 1 plus alpha copper minus alpha steel delta t minus alpha copper alpha steel delta t square. And then, we neglect this. And there your final answer is 1 plus alpha copper minus alpha steel delta t. Now, if you ask me, this is more accurate, but then again, exams may sometimes you'll see options like this. So you get it from binomial approximation. So be careful. All got this? So this is there. So whenever the temperature changes, right, this is one thing will happen. Your scales do actually get messed up. So the same instrument might work differently in the daytime and evening time. So that's why when you're doing an experiment, you have to make sure your lab conditions are same. Next one. Any doubts on this? Clear now, Ojas? Ansh? Adi? Clear with this? Arnav? Next one. We have a pendulum here. Alpha of the wire is 10 power minus 5 Celsius. This is a seconds pendulum. So when you hear the word seconds pendulum, meaning it's the time period is 2 seconds. So it takes 2 seconds to complete the oscillation. That is called a seconds pendulum. So you have constructed a clock which works properly at 30 degrees. So at 30 degrees, the pendulum clock gives you accurate time. Now, if you actually look at the formula, we know the time period T is given by, I will use small t. This I showed you in units and dimensions if you remember. T is equal to 2 pi root over L by G, where L is the length of the pendulum wire. G is the acceleration due to gravity. So when you increase the temperature, what will happen? Length of the wire will increase. If length of the wire increases, time period increases. That means your whole clock gets messed up again. So the question is, find the loss or gain of time. We don't know whether you're gaining or losing time. Find the loss or gain of time per day when temperature is 40 degrees. So if you use this clock at 40 degrees and you try to measure the time, will you lose time or gain time? And how much do you lose or gain per day? So you have to tell me two things: how much, and are you gaining or losing? So in the formula, time period L increases, G is constant. So if L increases, time period increases. So the clock doesn't work properly at 40, you'll get an error. So are you losing or gaining time? And how much is that per day? Question is clear, everyone? Think. Just give it a try. L into 10 power minus. Just convert that into seconds, right? So first the question is, are you losing or gaining time? What do you guys think? When you increase the temperature, length increases. If length increases, time period increases. Again, don't get confused. Huh? Time period increases, meaning what? Listen. How do you count time? When this pendulum completes one oscillation, you think it is 2 seconds, right? If it completes one oscillation, you will think it is 2 seconds. But now when the time period increased, let's say now it takes 2.1 second to complete the oscillation. But what will you think? It is 2 seconds now. Are you getting the point? When you increase the length, the time period for one oscillation increases. That means you think, right, even though the time is actually 2.1 seconds, you think it is 2 seconds. Meaning after some time, when the clock shows 1 hour, in reality, the time is 1 hour, 5 minutes, isn't it? So did you lose time or gain time? You lost time. The thing is taking more and more time to complete one oscillation. Meaning, if I have to give you an analogy, think of like this. Let's say if you have an employee who can finish off the work in 1 hour, for some reason he takes 1 hour, 5 minutes to complete the work. Did the productivity increase or decrease? Productivity decreased, right? You get less work done. You are losing work actually. So let's see how to calculate this. So one thing is clear, we're losing time. So 2 pi root over L by G. If you look at this, I taught you this in vectors. If you have A is equal to P power X, Q power Y, and R power Z. So from errors, if you see dA by A is X times dP by P, y times dq by q plus z times dr by r. This will be, so t will be 2 pi L by G whole power of. This will be dt by t is equal to half dl by L plus half dg by G. G is constant, so we can ignore this. So this formula becomes dt is equal to t by 2 dl by L. T is 2 seconds, it's a seconds pendulum. dl is L alpha delta t by L. LL will cancel. Alpha is 10 power minus 5 and this is 10. So we get dt is 10 power minus 4 seconds. What is the meaning of this? So the change in time period is 10 power minus 4 seconds per oscillation. So every oscillation has increased by this much time. So pendulum takes 10 power minus 4 seconds more to complete an oscillation. Right? Therefore, we lose time actually. So how much time are we losing? So we are losing 10 power minus 4 seconds per oscillation, right? But one oscillation is 2 seconds. It's a seconds pendulum. Therefore, we lose 10 power minus 4 by 2 seconds per every 1 second. Now for a day, we have 86,400 seconds and you're losing 10 power minus 4 by 2. This comes to around 4.32 seconds per day. There, you're right, Ansh. But it will lose time. That's why it's be careful. When time period increases, you lose time. If time period becomes smaller, you're finishing up the oscillation much faster. So we lose this much time. In a day, we lose 4.32 seconds per day. That means when the clock shows 24 hours, in reality, it is 24 hours, 4.32 seconds. So in a day, nothing happens, but in 100 days, that will be 40 seconds. In a year, that will be around 120 seconds. So within a year, you will start losing 3 minutes per day. Within a decade, that will be half an hour. Within 2 decades, you will lose 1 hour per day. So your timing will actually go back by one day. So in 240 years, your entire calendar will be shifted by 1 day backward. The error keeps on accumulating. Clear with this? There, this is the second thing that can happen. So one, your scales will get messed up, your times can get messed up. So even if you're using a wristwatch, right? Think about it. Even in a wristwatch or something, the needles and all, those are metal only, right? So when the temperature increases, what will happen? Even though they will expand and contract. So they do affect your time. All clear with this? Next one. Bimetallic strip. Now, when two different metals are welded side by side, and when temperature changes, And if you want them to be in contact, there's only one option, the rods bend. What do you mean by this? For example, so this is what you do. You take two strips, like let's say you take one copper and one iron, and you take this thing and you weld them. So this is copper. This is some steel sheet. Same length. Width is D. Right? And now generally we know copper ka alpha is greater than iron, meaning copper will expand more or contract more compared to this. And these red ones are the welding joints. Now, technically, if you try to increase the temperature, what should happen? The copper will try to expand more. Steel will become like this, na? But if this happens, what will happen? The joints will break. The joints will not let you expand like this. So now you tell me, copper has to be more than iron, but the joint should not break. What is the possibility? So if temperature increases, copper must be more than iron. There's only one possibility. You can be together, even though different lengths, is if you become a circle. Isn't it? The inner one will expand less and the outer one will expand more. So this will how it will look. This will be copper and this will be iron. Because copper expands more than this is how it looks. They'll form a circle like this. So length of the copper will be length of the iron. Suppose same thing, if temperature decreases, again same idea. Copper ka length must be smaller because it will contract more. Now the shape will change. Now it looks like this. So copper will be this. Now iron will be more. This was the question in the exam. L copper will be less than L iron. Most people blindly wrote this and came without even seeing whether the temperature increased or decreased. So it matters. So basically this thing is called a bimetallic strip. By two metals, metallic strip. So you keep them side by side and weld them up, and then you increase or decrease temperature, it bends. So what are the use of this? We can actually use this as a circuit breaker. Let's see how that works. See. So let's assume temperature increased. So this angle will be theta. This will be radius. This will be d. So we will consider, L is much greater than d because every layer will actually elongate different amounts. We want to neglect that. So this guy will be L into 1 plus alpha copper delta T, right? Which will be, we will see that how much is that. And this will be L into 1 plus alpha iron delta T. So from here you can clearly see R plus D into theta. The outer one has a radius of R plus D is L into 1 plus alpha copper delta T. This would be R into theta is L into 1 plus alpha iron delta T. Divide them, you will get R and you can get theta also. This is how you can find R and theta. So what is the use of this? Temperature decreases, you will write reverse. It will be 1 minus alpha copper and 1 minus alpha iron. So whoever has more alpha, when temperature increases, that guy should be outside. Clear, everyone? Now, how to use this thing? Let's say, you're making a If you ever gone for a the sauna or steam bath, nowadays we don't use this, but once upon a time it used to be like this. We have a circuit, we have a heater. So this circuit, right, is connected with a bimetallic strip here. Now see what happens. Let's say when the temperature of the room is 30 degrees, it is cold. You switch on the circuit, right? Then what will happen? Current is flowing through the circuit. The heater will produce heat. The room temperature will increase 40, 50, and let's say the moment it reaches 60. So if you look at this bimetallic strip, which is touching the wires, will suddenly bend. It will become like this. Circuit gets disconnected, no? Current will stop flowing. Current suddenly becomes zero. If current suddenly becomes zero, the heater will switch off. Then the temperature will start cooling down. 60 becomes again 55, 55 becomes 50, 50 becomes 45. Then again it becomes straight. Then again heater will switch on. You're getting the cycle. Temperature goes below 50 degrees, it will become straight. Temperature goes more than 65, it will bend. So automatically the circuit is getting on and off on its own, isn't it? And you can maintain the temperature of this room or that that steam bath or whatever at 50 to 60 degrees ka beech mein. So it's like a circuit breaker. Problem with this thing, mechanical systems, when it is bending and going straight, bending and going straight, these things have a life cycle. Maybe they can do this for 1,000, 2,000 times, and after that they won't work that efficiently. So we have to keep replacing them every 3 months or 6 months. Nowadays we don't use them, but we still use them in fire alarms. If you ever seen a fire alarm, right? So we have something similar like that, a circuit breaker. When the temperature of the room exceeds a certain temperature, this thing breaks off, the alarm starts ringing. So we use some kind of sensors and all. So bimetallic strips have a purpose. So this is what you can do. So basically this becoming straight and bending, we can use this phenomena to make it into a circuit. And because it is a metal, it's a good conductor. So it can act like a switch, which depends on temperature. Making sense? So a bimetallic strip is a switch which can go on and off, which works based on your temperature. Clear? Next thing. So that is about a bimetallic strip. Next thing, cavities. This is one good one, theoretical question. What happens if you have a cavity on a body and if you try to increase the temperature or decrease the temperature? So cavities or gaps. So when you have a cavity or a gap, so the gaps in the cavities behave as if they have same alpha as the surrounding material. What do you mean by that? Think of like this. Let's say we have a ring with a small gap. Let d be the width of the gap, and this is the radius r and theta. Now, the general confusion, what people think like this. So when I increase the temperature, right, this thing will expand and the gap will close down. It will come closer. Don't do that. Think like this. Consider full ring. Take a full ring. Okay? Take a red color marker and paint it. Don't cut it. Paint it. Now expand the ring. The red color marker also will expand. Now cut it. Do you think the gap increased or decreased? Gap increased, right? So the most common mistake what people forget now, what you're saying is right. Sir, these two will come closer, but you're also forgetting these two things will go away from each other also. It's expanding outwards also, right? So there's a net expansion. And not only that, look at the other reason. When a circle becomes from small to big, what is the total angle in a circle? 360, right? Does it depend how big the circle is? That means if this angle is theta, this also has to subtend theta only, na? Making sense? So the ratio still has to be maintained. So this is what will happen. The gaps will behave. The circle becomes big. The gap also becomes big. The theta will remain same. So radius becomes r into 1 plus alpha delta t. The gap also becomes d into 1 plus alpha delta t. So whenever you get a confusion, will the gap increase or shrink? Ask yourself. Make a complete shape. Take a red color marker. Mark that thing. Expand it. Then cut it. Are you getting it? Cut it after expanding. That way you'll not get a confusion with whether it is shrinking or increasing. But just to give you an idea, it will always increase. So all distances means if you take a body with some cavities and gaps or whatever, and if you mark 2 points, all distances change by a factor of 1 plus alpha delta t. So the cavity will behave as if it doesn't exist. I'll give you one more example. Even if body has cavities. But that logic is making sense. Take a complete circle, take a red color marker, mark that point, now expand it, then cut it. Now, if you think that way, you can clearly see the gap also has increased. Now, look at one more example. Let's say we have taken a sheet. We have a gap and we have a gap. This is A, this is B, this is C, and this is D. Now, when I increase the temperature, what will you think will happen between distance between B and C? If I increase the temperature, what happens to the distance BC? Increase, decrease. Now again, people think like this, sir, you told cavities also will increase. So this will increase, so gap decrease on again. Don't do that mistake. Imagine like this. Take a sheet, full sheet, right? Take a red color marker, make 2 circles. Now expand this sheet. It will become big like this. The circles also will become big like this, isn't it? Now cut the circle. Now, did you think the gap increased or decreased? Gap increased. So again, the same thing I'm saying, cavities will increase, but this BC material also will expand. Everything will expand. It doesn't matter, like, any point, you choose any 2 points, the distance will always increase. So when you increase the temperature, the sheet becomes bigger. The cavity also becomes bigger. The gap also increases. Everything increases. AB increases, BC increases, CD increases. AB, BC, CD. Every distance increases by a factor 1 plus alpha delta t. Whether you have a cavity, no cavity, it doesn't matter. Clear, everyone? There, that is one more thing about the cavities. Clear? Any doubts on this? Next thing. Areal expansion. If lengths increase, areas also will change. This chapter, right, actually has a little more connectivity to elasticity and all. So we will not be able to do all different models in this, but when other chapters keep coming up there, we will keep including. As such, the chapter is small. Next class, right, in the maybe the first half an hour or something, we'll wrap it up. And then we'll start off with something called calorimetry. School me did, na? Ice is mixed with water. What is the temperature? Those kind of questions. KTG is your ideal gas equation. PV is equal to nRT. So like I said, the first 3 are little easy. So if you take a sheet, let's say this length is L, this is alpha 1, this breadth is B, this is alpha 2. So a material, right, can have different alphas in different direction. These kind of materials are called anisotropic materials. Best example is glass. If you take glass and try to expand, right, it expands in different directions differently because inside the lattice is not uniform. This is an anisotropic material, meaning in three-dimensional, the lattice structure is not same in every direction. It's not uniform. Think of graphite. If you see graphite, right, layer by layer is fine, but between layer and layer, there is no interaction. So the 3D the structure is not same. So material has different alpha in different directions. If it's isotropic, meaning it is same. So when I try to increase this, this will become L into 1 plus alpha 1 delta T. This will be B into 1 plus alpha 2 delta T. So the new area, the change in area will be area final minus area initial, which is LB into 1 plus alpha 1 delta T, 1 plus alpha 2 delta T minus LB. So this would be LB. LB will cancel. We get alpha 1 plus alpha 2 delta T plus alpha 1 alpha 2 delta T square. We know whenever you get this thing, this is negligible. So your formula becomes delta A is equal to A into alpha 1 plus alpha 2 delta T. So we define this thing as delta A is equal to A beta delta T, where beta can be written as 1 by A into dA by dt. This is called coefficient of areal expansion. Just like alpha gives you length, this gives you about the area. And you can see here beta ka value is given by alpha 1 plus alpha 2. If material is isotropic, if alpha 1 is equal to alpha 2, then beta becomes equal to 2 alpha, where alpha is a coefficient of linear expansion. There. There's not much. It is just like, length. This is just for area. So if someone tells you like this is the area of a sheet is 2 meters square, find the change in area, you just use this. Clear, everyone? Same thing I can do for volumes also. So volume expansion is more important than areal expansion because you can use this for gases and liquids also. So volume expansion, we define something called gamma. This is coefficient of volume expansion. Same thing, we will take a cuboid. Let's say this is L1, alpha 1, breadth B, alpha 2, height gamma, beta alpha 3. So we get change in volume is equal to LBH 1 plus alpha 1 delta T, 1 plus alpha 2 delta T, 1 plus alpha 3 delta T. Now neglect all the higher power terms, you end up with delta V is equal to V into alpha 1 plus alpha 2 plus alpha 3 into delta T. This can be written as delta V is equal to V gamma delta T. So we can say gamma is 1 by V dV by dt. And gamma ka value is given by alpha 1 plus alpha 2 plus alpha 3. If it's an isotropic material, all are equal, then gamma will be 3 alpha. Quite a useful one. Now, examiner, they do ask questions like this. There was a question like this. They said volume V is equal to KT square, right? K is some constant. The question was find gamma. Now, from the formula, if you see, gamma is 1 by V dV by dt. So 1 by V is KT square and dV by dt is 2 KT. You get 2 by T. That was an answer. That was a question in the exam directly. So you should know about that. And if you look at this thing, for liquids and gases, alpha and beta are not defined. Linear expansion and aerial expansion don't make any sense. So only gamma is defined. That's where gamma becomes more important. For solids, will be alpha you can use. But when you talk about liquids and gases, gamma is the only thing that we have. There, have a look at this. But like I said, if you see everything, we're playing from that one equation only. Everything comes from alpha only. Clear with this? So if you take liquids and when you increase the temperature, so volume increases. Generally, volume increases. There are exceptions, but most of the cases they do work. So what gets messed up? Density. So based on this, we will get questions in fluid mechanics. So those questions we will see in fluid mechanics, so respective chapters. So we know density rho is given by mass by volume. So when you increase the temperature, mass doesn't change. So the new density will be mass will remain same, whereas the volume becomes V into 1 plus gamma delta T. This actually becomes rho old by 1 plus gamma delta T. So generally density does decrease rho naught by 1 plus gamma delta T. This is the variation of density. Most materials obey this. The solids are more denser than liquids. Water is an exception. Anomalous expansion of water. Meaning, I'm pretty sure you studied in chemistry. When water starts freezing into ice, it starts forming in hexagonal structures. And you get a lot of empty spaces. So there are air molecules, so overall density drops. Anomalous expansion of water. We will, if you try to plot the density versus temperature, the graph kind of looks like this. It peaks here and becomes like this. So this point is 4 degrees. This is ice here. So at 4 degrees, water has the maximum density. One of the reasons why there is a life on Earth. If the ice was actually more denser than water, you know what would have happened? Whenever there's an ice age, whatever ice forms on the surface will start sinking at the bottom. So the oceans will freeze from the bottom to the top. But what happens, because the ice is lighter, it forms a shield, kind of a layer on the top, and ice is a bad conductor. So the more thicker the ice becomes, more difficult for the heat to escape. Meaning, if you see now, in Russia and all, these rivers get frozen, right? Even if it is a very severe winter, when the temperature outside goes to minus 30, minus 40 degrees, and if the winter persists for 2-3 years also, right, the thickness of ice is only 1.5 meter. The entire river or lake doesn't get frozen to ice. The fish are still surviving. Meaning in Antarctica, right, we have ice thickness of around 1 to 2 kilometers. And you know how long it took them to form? 5 million years. It's very difficult to get ice. As the ice becomes thicker and thicker, it becomes exponentially difficult to create more ice. So one reason why actually the aquatic life survives, because the ice ages generally last for 20, 40,000 years, right? And still the oceans are not frozen. So density of water is 1 gram per cc or 1000 kg per meter cube. You should remember these values. It does change, but approximately we can equate it. But rho of ice is 0.9 gram per cc. There's a huge change. That's 900 kg per meter cube. That means if you take an ice cube, of 1 meter, we will have volume of ice will be 1 meter cube. When this guy melts and becomes water, mass will remain same. You get volume 0.9 meter cube. So it actually shrinks. So if you take a container full of ice and if you let it melt, then you will get almost 10% empty space in the container. Clear with this? So let me ask you a theoretical question. Let's say we take a container and you fill this with 4 degrees water completely up to the brim. Glass completely, or container completely filled with 4-degree water. Now, if I increase the temperature or decrease the temperature, in which case will the water overflow? If temperature increases or decreases, in which case water overflows. Both the cases, right? At 4 degrees, water has maximum density, meaning volume is minimum, na? Mass is same. Water has max density, therefore volume is minimum. So if you increase or decrease the temperature, both the cases volume will expand. Simple theoretical questions. There. So that is a little about the volume expansion and stuff. So next class when we catch up, we'll continue from here. We will see how does liquids behave when you put in a container, because container also will expand, liquid also will expand. So we will see what kind of issues we will get there. So after that, we'll start off with calorimetry. That is also a small chapter. I think next class we'll wrap up that also. It is all that only. Water is mixed with ice. So what is the new temperature? How much ice is left and all that stuff. So those are 2 small chapters. And after the next class, I'll give you a small sheet also on this because I think the questions are completely scattered everywhere and you might get other chapters questions also. I'll send you a small sheet like 20-25 questions. That much you do it is sufficient. Okay, so with that, we'll wrap up for the day, right? Remember, there's a test online till tomorrow, so do make sure to give it. So any doubts, anything, you can stay back and ask or else you're free to leave. So take care, stay safe. I'll see you guys again on Tuesday, same time. So where is this?